Okay, this is class example program unit D2 page 4. Okay, let's take a look at the program. A free jet of fluid comes in from left and strikes a wedge, and then this wedge has a 30 degrees of an angle. Of the total flow, a portion is deflected 30 degrees downwards here. This is the portion of incoming flow deflected downwards. The remainder is not deflected, which goes straight. Okay? The horizontal and the vertical components of force, FH and FB, needed to hold the wedge stationary. As you can see, these are anchoring forces, FH, FB. Okay? Gravity is negligible. Let's ignore the gravity. Okay? And the fluid speed remains constant. Let's determine the force ratio FH, FB. And also, I want to add one more thing to make it clear. Let's ignore also the viscosity. Okay? Let's move on to this side. So this is the same figure I copied from the program statement. This is the wedge, 30 degrees. So water jet comes in, goes out. Some portion of the incoming flow is deflected 30 degrees because of the presence of the wedge. Okay. Now, before we begin, let's just make a checklist. What type of forces do we need to include in this analysis here? One of them is anchoring force, oftentimes called reaction force. Equal and opposite to the force developed by this incoming fluid due to momentum, change of momentum. Okay. Then force due to pressure difference. And force due to viscosity. And force due to body force. Typically, body force really means the gravity. Gravity means how much weight do you have within, how much weight of water do you have inside of the control body. Now, the program statement clearly says that. Let's ignore the gravity. So this is 0. We can ignore that. Then I also, even though the program statement doesn't say, I want to clarify, let's ignore viscosity. Let's ignore the friction due to viscosity, also 0. Okay? Let's ignore that. Do we have a pressure difference between in and out? Well, this is a free jet. Once again, pressure is always 0 gauge everywhere. So this is also 0. So once again, the force you are going to include in this analysis is just anchoring force FH and B. Those two forces. Okay. So let's begin with setting up the coordinate. Okay. So obviously this is x direction, and then since we are ignoring the gravity, oftentimes we want to choose the coordinate z, which is against the direction of gravity. In this case, we ignore the gravity anyways, so I choose my coordinate y. So I'm going to make xy plane. Okay. Of course, you can choose x and z, z being opposite direction to the gravitational acceleration. That's fine too. But I'm going to just simplify it, x and y direction. Okay. All right, now I'm going to define the control volume, which is fixed. So I'm going to include wedge and regen of water. Now here, let's be careful about that. Okay? I'm going to choose the control volume, which is one of the control surfaces completely perpendicular to outgoing flow. If you choose the control volume just like so, straight out, that's going to make you one more analysis added on. This is the direction of velocity. this is the direction of outward unit normal flow, you have to figure out what's the angle between them, which is 30 degrees, which is added complication. I don't want to do that. So let's be careful when you choose control volume. Let's choose the best control volume, minimizes your work. Okay. So this is fixed control volume. So for this control volume, you are going to set control surface right here. Let's call this control surface 1. Right here, this is control surface 2. Okay. This is a better decision than choosing this kind of control surface. The reason here is, like I said, obviously, this is going to be outward unit normal vector direction, which lines up with velocity vector, which makes you easy to take a dot product. Okay. Let's call this control surface 3. So at each control surface, you're going to define outward unit normal vector. This is N1. This is N3, this is N2. Inflow, out, out. So one inflow, two outflow. Okay, good. And let's just apply momentum equation. Okay. So momentum equation, let's begin with governing equation form. ddt integral over control volume v rho dv plus integral over control surface v rho v dot nda is equal to summation of the force. This is once again steady flow. So this term drops off. So the now the equation becomes integral over Cs v rho v dot n dA is summation of the force. Obviously this one actually has two components in x and y direction, and also you have to apply control surface in 1 and 2 and 3. So this now becomes two equations with the 3 control surfaces. So let me just open up. So one of them is x momentum. So let me just come up with x momentum equation. This is going to be okay, integral control surface 1 u1 rho v1 dot n1 dA1 plus integral cs2 u2 rho v2 dot n2 dA2 plus integral cs3 u3 rho v3 dot n3 dA3 is equal to the force in x direction. Well, let's be careful. This is negative fx because it's a negative x direction, right? So let's be careful. This is negative fh. Negative sign. This force direction-wise, it's in negative x direction. Let's be careful. So this is x momentum equation. All right. How about y momentum? Y momentum equation, again, similarly, it's going to be integral over control surface 1. B1 rho. B1 dot N1 dA1 plus integral control surface 2. B2 rho. B1 dot N, not B1, B2 dot N2 dA2 plus integral over control surface 3 B3 rho B3 dot N3 dA3 is equal to FB, positive FB. Okay. So you get x momentum, y momentum equation, right? Of course, I don't have to emphasize, but keep in mind, note, velocity is a vector. So in this case, this is xy plane. So velocity has an x direction component u multiplied by unit vector in x direction plus velocity component in y direction and unit vector in y direction. So this is a general expression of velocity as a vector. I'm just choosing x component and y component. Okay. So you come up with the two equations, x momentum, y momentum equations. Right? Well, that's good. So what I want to do here is, again, you don't have to do this if you get used to it, but I'm going to make up a table once again. It's going to be bigger table because we have 3 control surfaces. Control surface 1, control surface 2, control surface 3. Okay? At each control surfaces, you are going to figure out what is U1, what is U2, what is U3, what is B1, what is B2, what is B3, what is B1 dot N1, what is B2 dot N2, what is B3 dot N3. So you want to figure out each control surface's property one by one. Let's take a look at one by one. U1. Okay, this is velocity vector B1. This is velocity vector B3. This is velocity vector B2. Okay. Before we move on, let's take a look at the problem statement once again. Okay. So make sure we read through the problem statement very carefully. One of the important hints here, actually a very important statement defined here is, okay, somewhere. Oh, the fluid speed remains constant. This is super important comment. So that means magnitude of velocity v1, which is b, doesn't change. Doesn't change. So magnitude-wise, velocity is always b and b and b. Magnitude-wise, okay? So, having said that, let's go back and take a look. Okay. So, what is u1 equal to? u1 is, like I said, this b1 is u1i. Velocity is only in x direction. So u1 is essentially magnitude of v1, which is b. B. Magnitude of v1. What is v1? Velocity is a y direction component, none. This is 0. Ooh, interestingly, if this is 0, this whole thing is 0. Good. I can simplify a little bit about this y momentum equation. B1 dot N1, if you take a dot product between those two, it's going to be negative of magnitude of B1, so this is minus B. Good. Okay? So what about, oh, skip here. Let's take a look at this one. This one's kind of similar to that on the outflow. What's U3? U3 is magnitude of B3. So this is, once again, this is U3I on the x direction component. So this is the magnitude of B3, which is B. Huh. What's B3? Oh, there's none. So this is 0 again. Oh, that means this whole thing is 0. Good. B3 dot product N3 is, again, positive of B. Simple as that. So we have to be very careful about control surface 2. Let me just redraw control surface 2. So let's just take a look at the situation here. So this is control surface 2. Velocity has two components. Okay. So you have x direction component, y direction component. So this is U2I. This is B2J. Velocity B2 is U2I plus B2J. So you have both U2 and B2, non-zero. U2, what's U2? U2 is, it looks like, this is 30 degrees. So sine 30, so that's B cos 30. Oh yeah, that's right. What's B2? Magnitude of B2 is B sine 30. Very common mistake. This is not correct. Let's stop and think again. What is the magnitude of B2? This is B2, which is this sine 30. What's wrong with it? Oh, something wrong, because the direction of this B2 is opposite direction of y, so do not forget minus sign. Minus B sine 30. Very common mistake, lots of people make this mistake. If I happen to choose this as a final exam, I can guarantee probably more than half of the class do make this mistake. But if I emphasize in this video, I hope it is going to minimize that kind of mistake. But minus sign. It's really easy to make this kind of mistake. Let's be careful. It's minus direction of y, so it's minus sign. Okay. Anyway. If you take a dot product B2 dot N2, it's the same direction vector, it's just a B, right? Same thing. So, having done that, what's next step? Well, next step, I want to apply, let's take a look at continuity. Continuity equation. Let's apply continuity. ddt integral cb rho dB plus integral cs rho b dot nda is equal to 0. Oops. This is a steady state. This one, once again, this is water, so it's liquid. So density is constant, so it goes outside of integral. You can divide both sides by density. Density goes away. So simple deal is Cs B dot N dA is 0. If you apply this to 3 control surfaces, similar deal. So this is control surface 1, 2, 3 applied. This is continuity. So B1 dot N1 is minus B, integrated over the area A1. Right? B2 dot N2 is just a B, integrated over A2. Right? B3 dot N3 is just a B, integrated over A3 is equal to 0. So this is essentially Q1, Q2, Q3. This equation really tells you minus Q1 plus Q2 plus Q3 is equal to 0. Whatever the incoming flow is equal to whatever the outgoing flow. Flow in terms of volume is equal to flow out in terms of volume. Volume flow rate in is equal to volume flow rate out. So this equation really tells you Q in is Q out, right? Very familiar form of continuity. Okay, but interesting thing about it is we do know the velocity doesn't change. The problem says so. So you can multiply both sides, well, you can divide both sides by velocity. Takes this out. Cancel out. Okay. Conclusion. Well, minus A1 plus A2 plus A3 is equal to 0. Oh, what do you mean by that? That means A1 is equal to A2 plus A3. This is quite interesting equation. Let's call this equation 1 because it's coming from continuity. Okay. Now this equation tells you the following. Let's go to here. Okay. So that continuity really tells you that whatever the cross-section area CS1 is equal to the control surface 2 and 3 cross-section added together becomes this. Okay? A very simple deal. So essentially some portion of the flow is going down, the remaining portion of the flow goes away. If you add them up, it's going to come up with the same cross-section. Yeah, that's what the continuity says. But this is quite important information, okay, later on. All right. So, I'm getting worried about this empty space here, if it's enough or not. So, I'm going to finish up X momentum and Y momentum, okay? So let's go back to X momentum. Okay, so X momentum equation, let's revisit. Let's take a look at it. U1 is V. Density is rho of water. I know this is constant. V1 dot N1 is minus V. Integrated over cross-section area A1, so this is A1. Okay? Plus. Now this time, U2 is equal to B cosine 30. Density is rho. B2 dot N2 is B. Cross-section area A2. How about U3? U3 is B. Density is rho. B3 dot N3 is B. Again. Integrated over A3 is equal to minus FH. Okay. So let's just simplify this equation a little bit more. If you simplify this equation, you end up having this kind of equation. Okay. Minus B squared rho A1 plus B squared cosine 30 rho A2 square rho A3 is equal to minus FH. So this equation is coming from X momentum. Let's call this equation 2. So now we have equation 1, equation 2. Good. Next, what about Y momentum? So I'm going to revisit Y momentum equation right here. Obviously, we simplified this term, that term drops off because B1 is 0, B3, 0 also. So this drops this term, that term. So only this term remains. So Y momentum is, B2 is minus B sine theta. Once again, very, very common to forget about this minus sign. Let's be careful. Density is rho. B2 dot N2 is B. If you integrate over cross-section area A2, this is going to get you A2. This is going to be equal to FB. Now I'm going to bring this minus sign to right hand side because what I'm going to do is to find out the ratio between FH and FB. Okay, so I'm going to change this form a little bit. This is going to be B squared sine 30 sine 30. Theta is 30 degrees. Okay, sine 30 rho times A2 is equal to minus FB. I'm going to purposefully bring the minus sign to the right hand side because if you take a ratio between these two equations, minus sign goes away. This is equation 3, right? So what I'm going to do, taking ratio means average equation 2 divided by equation 3. Let's do that. So equation 2. This is going to get you ratio of FH over FB. Right? It's minus sign goes away, okay? Now, minus B square rho A1 plus B square cosine 30 rho A2 plus B square rho A3 divided by that B square sine 30 rho A2. Okay, so we are going to simplify this a little bit more. I can say it looks like B square rho is all common. So you can cancel out B square and rho. B square and rho goes away. So this is going to be minus A1 plus A2 cosine 30 plus A3 divided by A2 A2 sine 30. Can we simplify a little bit more? Yes. Well, what is A1? Because A1 is A2 plus A3, right? So let's just combine equation 1 to that. So that means this is minus A2 plus A3 plus A2 cosine 30 plus A3 A2 into sine 30. Well, if we do that, automatically, this is minus A3, this is plus A3, this is cancelled. A3 is gone, so that actually remaining only A2. So this is going to be A2 cosine 30 degrees minus 1. A2 sine 30. Now, you can cancel A2 out. So this is really cosine 30 degrees minus 1 divided by sine 30 degrees. If you pick up your calculator and calculate cosine 30 minus 1 divided by sine 30, you are going to get the value of minus 0.268. Oh, why you got minus? Whoa, there's something wrong here? No. Why you got this minus sign? Let's go all the way back to the original figure. So that really means that one of the original gas, direction-wise, is opposite. So let's think about that. If you have a wedge of 30 degrees and water is incoming from left to right, how do you support this wedge? You are going to support from right to left, and you're going to support from top to bottom. It's not going to support like this. So this is actually wrong direction. This should be the direction of FB. So that minus sign confirms that the initial gas, the direction of anchoring force was wrong. So you are going to quickly correct it, okay, at the very end, okay? So, that's it.